Hello students, welcome back. So now in this session, I'm going to be talking about stochastic gradient descent and also mini batch gradient descent. I'm going to compare that with full batch gradient descent. So what exactly is a gradient descent? Well, gradient descent, it is an optimization algorithm. And what it does, it minimizes your loss function. Another name for loss function is error function. And the way it minimizes the loss function is by updating your model parameter. So suppose you're working with a linear regression model right here. This is a linear regression model. So in this case, we try to find this M and B. That is this M and this B, and we try to find this m and b in such a manner so that your loss function, that would be this right here, it is minimized. In other words, this loss is as minimum as possible. If you recall from your gradient descent class, your loss function is for this particular instance is going to be equal to 1 divided by the total sample size summation of true value of your y minus the predicted value of your y, and then you square that and then you add them all together. So this is your loss function. And the idea is this, that you calculate the slope of your loss and you move these parameters, this m and b, in a direction that is opposite to the slope. And then you keep repeating this until your error becomes minimum. So this is the idea of your gradient descent. Now in your gradient descent, these are your errors. So let's say this is my y1, this is the actual value, and this is the y predicted. So based on this equation, y bar with y hat equal to mx plus b, this is my predicted value. So this difference right here, this is my error 1. And likewise, let's say this is my y3, and this is the predicted value for y3 for this particular y. So in this case, this will be my error 3. Let's say this is my y2, and this is the predicted value. So this one would be your difference. So all these differences, these are your errors. That's what these terms are. These are your errors, and I'm just squaring these errors. Now, the full gradient descent, another name for that is batch gradient descent. And the idea is this, that you use all the training data to compute the gradient before you update your parameters. And this is the working algorithm. So I'm going to show you step by step. Suppose we assume some data set. This is your data set right here. So these are my feature X right here. In this case, I'm just taking one column feature, and this is my prediction right here, Y. So the step one, you initialize your parameters. Well, suppose we are working with the linear regression model. If you remember, in your linear regression model, your y would be mx plus b. This is the equation that will come out to be. That's what you're trying to predict. In other words, you're trying to find m and b. So we start with a random number. We pick up a random number of m, we pick up a random number of b. This is how we initialize our parameter. And then step 2. Now we are going to go in a loop until we converge. So step 2.1, that would be the first part. So you predict for all data the value of y. We know our m, we just initialize that. We already know our b, we initialize that. And we know our xi, that would be x1, x2, x3. So for each one of them, we find a predicted value of y. So let's say your y predicted, I'm going to call this y predicted right here. It comes out to be, let's say, 7 over here. Let's say this is 9, and let's say this is 11. These are my y predicted. Step 2.1, I'm going to compute the loss. So the loss is going to be equal to 1 divided by the total sample size. In this case, let's say my sample size is, let's say 3 in this case. So it's going to be 3 right here. And this one is going to be the difference between your actual value minus the predicted value. So in this case, the difference between y and 7. This is my actual value, and this is the predicted value. So the difference between y and 5 and 7 is 2. Okay, so this is going to become 2 square. Then the difference between 7 and 9, okay, this is going to become 2 again, so 2 square. I'm going to add them all together, and the difference between 8 and 11, that'll be 3 square. 3 square, and then you add them all together, whatever your answer is, and then you divide by 3, and this is what's happening over here. This is your loss function. Okay, then step 2.3. After this, we compute the gradient using all the samples. So here, I'm going to calculate my derivative of L with respect to M. It will come out to be this expression. And likewise, compute your derivative of L with respect to P. This is your answer right here. And these ones right here, they will be some numbers right here. This will also be some number. And now I'm going to be update my parameter once. I know my old value of M. I'm going to take alpha value. This is your learning rate. And then I know my alpha, del L by del M. This is the one I calculated in the previous step. So substitute your value and you'll get your new value of M. Likewise, you substitute your old value of B, substitute your alpha. This would be your learning parameter, and substitute this value that we got from the previous step. And this will give you your new value of B. So now we have received a new value of M and B. So this is one forward pass. In other words, this is one epoch that we just performed. We just took the whole data set and we found M and B. And then we repeat this process multiple times. Here, your one update, it basically translates to one full data set pass, and that would be equal to your one epoch. Now this one is very slow for large data set. Also, it consumes high memory. And that's because of this. Let's understand this through a simple example. Suppose I have 100,000 samples. Then we are going to be performing forward pass for 100,000 samples. And we have to calculate loss for 100,000 samples. And all this information needs to be stored somewhere. That's why it has a high memory loss. Also, suppose we have 10 features, then we would have to compute 100,000 times 10. That means 200,000 derivative, and that is just for one pass. And we have to do this thing for many passes, and that requires a lot of computation. And now comes the stochastic gradient descent. And the idea is this, that instead of using all the data at once, you update your parameter using only one training example at a time. And now let's look at the algorithm for the stochastic gradient descent. Step 1. Initialize your parameters, just like we did before. So you to pick up a random value of M, pick up a random value of B. Step 2. Now you shuffle your data set. You want to shuffle it in order to avoid bias. And then step 3. Now for each sample, let's take a look at this one right here. So I'm going to be repeating this for each one of these samples. I'm going to predict your y value. So I'm going to say y equal to m times xi plus b. So let's say I'm working with this sample right here. So I'm going to make a prediction of this one right here. Then you compute the loss for this one single sample. That would be this sample right here. So let's say the loss comes out to be this right here. Then you compute your gradient. This would be a single point, and your gradient comes out to be, let's say, these numbers. So this is just for one single point. Let's say this point right here. And then you update your immediately. You update your M and you update your B. You know your old value of M, you know your old value of B, you know your alpha, and you know this value we just calculated from the previous one, and this way you update M and B. So in this case, your parameters, your M and B, they change after every single sample. And step 4, now we move on to the next random sample. So the first one we picked up was this one, and let's say the next random sample would be this one, and we keep repeating this process. Now in this particular instance, we are performing many small updates instead of one big update. Now in full batch gradient descent, we approach minima smoothly, but it is slow. So in in stochastic GD, we approach minima in a zigzag path because we are randomly taking points. But in this case, it is fast. So this is a pictorial representation that helps you understand these concepts. So here, in this case, this is my full batch GD right here. This is my minima, and I would approach my minima in a smooth manner like this. On the other hand, in the case of stochastic gradient descent, I will be approaching my minima in a zigzag manner right here. And the reason I'm going zigzag is because I'm taking these random points. Now let's take a look at some of the advantages of stochastic gradient descent. Well, efficiency. Well, because it only uses one or few data points to calculate the gradient. So in this case, SGDB can be much faster, especially when you're dealing with large data sets. So here, each step, it requires fewer computation. It leads to quicker convergence. Also, you can escape a local minima. So when you're using SGD, the noisy, because you're going through the noise, so your point can jump from here to here, and from here it can jump over there, so it can actually escape your local minima. Now your SGD, it is well suited for online learning where your model is trained incremental as your new data comes in, so rather on a static data set. Also for memory efficiency, since it does not require storing the entire data set in your memory for each iteration, your SGD can handle much larger data set than your traditional gradient descent. Now, this is a small comparison between full gradient descent and stochastic gradient descent. In my full gradient descent, the data used, I will be using entire data set. In my stochastic, I'm using only one sample. Updates. In my full gradient descent, the updates is going to be few updates. Here, there are going to be many updates, and that's because I'm taking one sample at a time. Speed. Well, in full gradient descent, it tends to be slower because I'm actually loading and working with the whole data set. In this case, I'm only working with one sample at a time, so it is fast. How about memory consumption? Well, in full gradient descent, it has a high memory consumption because you are computing and working with the entire data set in one epoch. Here, you're working with one sample at a time. So memory consumption over here is low. Large data set, well, if you're working with large data set, your full gradient descent, they tend to be poor because it has to work with the whole data set in one single shot. Here, this is excellent because it's working with one sample at a time. Also, does it escape the local minima? Well, full gradient descent, it can be hard. On the other hand, stochastic gradient descent, it can escape local minima easily. And now you have mini batch gradient descent. So this one is used in industry. And the idea is this: instead of working with all the samples or one sample, we are working with only a small group of samples. This small group of sample, it has a name. It is called batch. The batch size, it can be either 32 samples, it can be 64 samples, or it can be 128 or 256 samples. So the algorithm for mini batch descent is like this. Step 1, you initialize your parameters. So pick up your M, pick up your B, let them be some random numbers, pick up your learning rate alpha, and also specify your batch size. That would be my K. So suppose I have 1000 samples, and suppose I pick K equal to 10 batch. Step 2, you shuffle your data set. Step 3, you split your data into mini batches. So here we have 1000 samples and we want 10 batches. So each batch is going to have 100 sample. So your batch 1, that will have 100 sample. So suppose this is your batch 1, that's going to have 100 sample. Your batch 2 is going to have 100 sample, batch 3 100, and likewise all the way up to batch 10, that's going to have 100 samples. And then step 4, for each mini batch, we are going to be performing following steps. Suppose your batch contains K samples. So step 4.1, predict for each batch. You make a prediction right here. So M times your X batch refers to like your all the X values from your batch, and you find your Y right there. So this is my Y predicted for that batch. So in this case, I'm computing prediction for all the K sample. That's what this batch contains. Step 4.2, you compute your batch loss. So for this one batch, you find your batch loss. That batch loss would be equal to 1 over K. This is the size of the batch, summation of yi minus y batch square. So you're just calculating the difference between your actual value and the batch value, and you're just squaring these values. Now here, only the batch data is used. Now, step 4.3, you compute gradients. In other words, you find the batch average. So you find the derivative, the partial derivative of your loss function of the batch with respect to M. That would be this right here. This is going to give you some number right here. Likewise, you calculate the partial derivative of your loss function of your batch with respect to B, the parameter B. That's going to give you this number right here. Step 4.4, now you update your parameter. You know your old value of M, you know your alpha, you know this number is basically this right here, and this way you can calculate your new value of M. You can do the same thing with B. This is your old value of B, you know your learning parameter, you know this value, this actually is from here, and now you know your B right here. Okay, this update happens after each mini batch. Step 5, now you move to the next batch, and you keep repeating this until all batches are finished. In other words, when all batches are finished, that will be called one epoch. So one epoch is done. And then you repeat this process many epochs. Now, a few things I want to say about the batch size. If your batch size is small, then it's going to be a better generalization. If your batch size is too large, it's going to be a poor learning. On the other hand, if you pick something in between, let's say large, it's going to be a faster computation. And now let's compare our batch gradient descent with our stochastic gradient descent and our mini batch gradient descent. So data used. Well, in my batch gradient descent, I used all the data. In the stochastic gradient descent, I only used one sample. In this particular case, I used a small batch. Speed. Well, your batch gradient descent, it tends to be slower. SGD, very fast. This one is in between right here. Stability. This is very stable. It's going to reach the minima. This can be noisy because it's going to reach in a zigzag manner. This is more like balance. This is like a balance between stable and noisy. GPU friendly. This is not very GPU friendly. This is poor. Well, that's because it takes the whole data set. This is also poor because it's working one at a time. Now, this one is excellent because you're working with small sample. Let's say you're working with 32 sample, 256 sample size, that's fine. Industry usage, bad GD, it tends to be rare. SGD, also rare. This one is a standard in industry.